Welcome to the deep dive. Today we're doing something a little bit different, shifting gears to bring you a special edition of the analysis explicitly titled the OriGene Technologies Podcast.
Right, which is really exciting.
Yeah, it is, because normally, we take a whole stack of articles and just sort of see where the story takes us. But today we actually have a really specific mission.
We do. We're partnering with OriGene Technologies to unpack one specific, highly impactful research publication. But we're also we're pulling back the curtain on the actual molecular tools that make this kind of discovery possible in the first place.
Exactly. So our goal today is to summarize this fascinating paper regarding type 2 diabetes and a very specific, maybe slightly controversial type of exercise training.
Oh, definitely controversial in some circles.
Right. And while we do that, we're going to highlight exactly how OriGene products were used to validate the findings. Because, as we always say, if you can't measure it accurately...
It didn't happen. That is the golden rule of the lab.
Yeah.
You have to be able to quantify it.
Exactly. So I want to start with a question for you, and really for everyone listening to this. When you think of building muscle, the classic image is the bodybuilder workout.
Grunting, straining,
Yeah.
the heavy barbell bending.
Yeah, exactly. Veins popping. And that works, right? We know it builds muscle.
Oh, it absolutely works. High-load resistance training is the absolute gold standard for hypertrophy, no question.
But what if I told you there's a way for you to get those exact same muscle-building benefits, the size, the strength, but using weights that are, well, honestly kind of pathetic, like lifting your grocery bag's level of weight?
It sounds like a late-night infomercial. Get ripped in 5 minutes with this one weird trick.
Right.
But in this case, that trick is actually backed by some seriously robust physiology.
Yeah.
So the paper we're looking at today is titled Blood Flow Restriction Resistance Training Improves Skeletal Muscle Mitochondrial Capacity and Cardiovascular Risk Factors in Type 2 Diabetes.
Quite a mouthful.
It is.
So,
It was published in Cell Metabolism in 2026 by Nina Tranks and her colleagues.
so this is right on the cutting edge. But before we get into the whole, the how of it all, we really need to talk about the who. This study focused entirely on people with type 2 diabetes. Why target that specific demographic?
It's a really critical group to study because type 2 diabetes isn't just a blood sugar issue. It fundamentally is a muscle disease.
A muscle disease.
Yeah. Patients often suffer from sarcopenia, which is this progressive, accelerated loss of muscle mass. And on top of that, their mitochondria, the actual power plants inside the cells, are deeply dysfunctional.
So they're essentially losing the engine and the fuel efficiency at the exact same time.
That's a perfect way to conceptualize it. Now, normally a doctor's prescription would be to go lift heavy weights, what we call CREST or conventional resistance training. You need to lift, around 70 to 80% of your one repetition maximum to trigger that muscle growth.
Sure, but if you're a 65-year-old patient with diabetic neuropathy, maybe you've got bad knees or high blood pressure.
Putting 200 pounds on your back to squat is a terrible idea.
Yeah, right. It's totally unsafe or just mechanically impossible for them.
Exactly. So the clinical dilemma researchers face is this: how do we get the incredible muscle adaptation of heavy lifting, but without the dangerous heavy load? And that is where the challenger steps in. Blood flow restriction training, or BFRT.
Okay, let's set the scene for the listener. Imagine I walk into the lab to be part of this BFRT group. What exactly are you doing to me?
Well, first, we hand you a very light weight. We're talking maybe 30% of your max. So if you can normally leg extension 100 pounds, we're giving you 30.
That would feel incredibly easy, like I'm not even working out.
For the first few reps, absolutely. But here's the catch. The researchers place a pneumatic cuff. Think of a really high-tech blood pressure cuff right at the top of your thigh. And they inflate it just enough to restrict the arterial blood flowing into the leg by about 60%.
Okay, so less fresh blood coming in.
Right. But crucially, they fully occlude or block the venous blood flowing out.
So the fresh blood kind of trickles in, but the used blood is just trapped there.
Precisely. And that changes the entire environment. Because the blood can't escape, all these metabolic waste products accumulate incredibly fast. Lactate, hydrogen ions, the environment inside your muscle becomes highly acidic.
Oh, wow.
And because that fresh arterial blood is restricted, the oxygen levels plummet. The muscle becomes hypoxic.
So you're basically creating this highly stressful, acidic, low oxygen environment inside the muscle, all while lifting what feels like a feather.
Stressful is the key word there. This intense metabolic stress actually tricks your brain. Your nervous system senses this extreme chemical environment and assumes, wow, we must be moving a literal mountain right now.
Because normally you'd only get that much acid buildup if you were maxing out.
Exactly. So the brain responds by recruiting the big guns. The high-threshold motor units, your type 2 muscle fibers, which are typically reserved only for maximum effort heavy lifting.
It's a biological lie. You're hacking the nervous system.
You really are. And so the entire point of this study was to see if this physiological hack could stand toe-to-toe with traditional heavy lifting over a 12-week supervised training period.
Okay, and they had 20 participants with type 2 diabetes, right?
Yeah.
Split into these two groups.
Yes, the heavy lifters doing CREST and the cuff lifters doing BFRT.
Let's get right to the scorecard then. Let's talk about muscle size and strength. Who won?
This was the first major surprise of the paper. It was a dead tie.
Wait, really? A tie?
A statistical draw. The researchers used MRI scans to meticulously measure the cross-sectional area of the quadriceps. Both groups gained roughly 4 to 5% muscle mass.
Wow.
And then they tested leg strength on a dynamometer, testing extension and flexion. Both groups got significantly stronger, and there was absolutely no statistical difference between lifting heavy and lifting light with a cuff.
That is just wild to think about. So you're telling me a patient with severe joint issues can lift a fraction of the weight, save their joints, and get the exact same structural hypertrophy?
Yes. It proves that mechanical load isn't the only driver for muscle growth. Metabolic stress is a massively powerful alternative. Though I do want to add a quick caveat about the experience.
It hurts.
It is not comfortable. That deep burn you feel at the very end of a brutal set of squats, you feel that almost instantly with the cuff. It definitely requires some mental fortitude, but mechanically, it's gentle on the joints.
Okay, so we've established the muscles got bigger. But as we discussed earlier with diabetes, size is only half the battle.
Yeah.
It's really about muscle quality, specifically the mitochondria.
Yes, the power plants.
Right. So let's talk about the mitochondria. How did the two workouts compare there?
This is where BFRT actually pulls ahead. This is the absolute core finding of the paper. Heavy lifting built the muscle, sure, but it didn't do much of anything for the mitochondria.
Really? I always assumed any hard exercise upgraded your mitochondria.
Not inherently. Heavy resistance training is primarily anaerobic. It doesn't force the aerobic machinery to adapt all that much. But the BFRT group, because of that hypoxic low oxygen state the cuff created, those cells were literally starving for efficiency.
So they were forced to adapt.
Exactly. The low oxygen triggers specific pathways like PGC1 alpha and AMPK that tell the cell, hey, we need more energy efficiency right now, build more mitochondria. And the study found that skeletal muscle mitochondrial oxidative capacity, specifically complex I and complex I plus I, increased significantly only in the BFRT group.
So they didn't just build a bigger engine, they built a vastly more efficient one.
Yes. They measured citrate synthase activity, which is a very reliable proxy marker for mitochondrial content, basically a head count for mitochondria.
Okay.
In the BFRT group, that activity skyrocketed by 109%. In the conventional heavy lifting group, no significant change.
109%. I mean, that's basically doubling the mitochondrial capacity. That is a massive number.
It is massive.
And this is where I want to put my skeptic hat on for a second. Because in science, big numbers make great headlines. But how do we actually know they're real? You can't just throw a muscle biopsy under a standard microscope, eyeball it, and say, yep, looks like double the mitochondria to me.
You absolutely cannot. And frankly, this brings us right to the methodology and to the reason we are explicitly highlighting this paper on the OriGene Technologies podcast today.
Right, the tools behind the discovery.
Exactly. To definitively claim that mitochondrial DNA increased, you need an incredibly precise ruler. You have to accurately quantify the ratio of mitochondrial DNA mtDNA to nuclear DNA nDNA.
Oh, I see. It's like doing a city census. You need to count exactly how many houses are in the city, the nucleus, before you can accurately calculate how many solar panels are on the roofs, the mitochondria.
That is a brilliant analogy, yes. And to execute this census, researchers use a technique called quantitative real-time PCR. But for that machine to give you a real number, it requires absolute physical standards to compare the biological samples against. You can't just use an algorithm to guess.
You need a physical baseline.
You do, and this is precisely where they integrated tools from OriGene Technologies.
Okay, walk us through this. What specific products did the lab use?
So they needed two distinct reference points.
Right.
First, to count the houses, the nuclear DNA baseline, they utilized an OriGene human LPL plasmid,
LPL.
lipoprotein lipase. It's a reliable single-copy gene found in the nucleus. And for the researchers listening who might actually want to replicate this assay, the specific catalog number is RC203766.
RC203766.
Got it. By using this specific plasmid, they generated a flawless standard curve that told them exactly how many nuclei they were looking at in any given sample.
Perfect. So they have the baseline. How do they measure the solar panels?
For the mitochondrial side of the ratio, they used the OriGene human ND1 plasmid. ND1 is a gene encoded exclusively within the mitochondrial DNA.
And the catalog number for that one?
That is SC101172.
So by comparing the signal from the ND1 plasmid to the signal from the LPL plasmid, using these OriGene products as the absolute ground truth, they were able to calculate the exact mitochondrial copy number per cell.
Precisely. Because they used these high-quality, sequence-verified plasmids to build their standard curves, we know that the 109% increase wasn't just background noise or a PCR artifact. It was a genuine, measurable biological adaptation.
That level of rigor is just so satisfying. And using this exact quantification method, they actually uncovered something else, didn't they? Something outside of the muscle entirely.
Oh, this was the finding that made me literally sit up at my desk. They took biopsies of adipose tissue body fat, and they found that the mitochondrial DNA increased in the fat tissue as well, but again, only in the BFRT group.
Wait, the fat tissue itself started building mitochondria, it became more metabolically active?
It appears so. The extreme metabolic stress isolated in the leg muscle somehow signaled the surrounding adipose tissue to wake up. It's a process often called the browning of fat taking, inert white storage fat, and shifting it toward metabolically active beige or brown fat.
That's incredible.
I get, to be clear, making a claim about mitochondrial changes inside adipose tissue is notoriously tricky. They only had the confidence to publish that finding because they utilized that robust OriGene LPL and ND1 plasmid quantification methodology.
Speaking of adipose tissue, let's talk about body composition overall. Because at the end of the day, fat loss is a massive priority for anyone managing diabetes. Did the study show a difference between the groups there?
It did, and it's a really nuanced difference. Both groups lost a similar small amount of total weight. But the physical location of where that fat was lost from was radically different.
Location is everything.
Right. The conventional heavy lifters lost more subcutaneous adipose tissue, or SAT. That's the fat located right under your skin, stuff you can physically pinch.
Right, the stuff people usually focus on for aesthetic reasons.
Exactly. But the BFRT group, they actually didn't lose much subcutaneous fat at all. Instead, they uniquely and significantly reduced their visceral adipose tissue, or VAT.
And for anyone who might be rusty on this, remind us why visceral fat is the one you really want to lose.
Visceral fat is the dangerous fat stored deep inside your abdominal cavity. It wraps directly around vital organs like your liver, your pancreas, your intestines, and it's not just a storage depot. It is an active endocrine organ.
Pumping out bad stuff.
Yes, it constantly secretes inflammatory cytokines. It is directly, causally linked to insulin resistance, cardiovascular disease, and overall mortality. Reducing visceral fat is arguably the single most important physical change a diabetic patient can make.
And you're saying the lightweight cuff workout melted the visceral fat, while lifting heavy weights did not.
That's what the data showed. The BFRT group reduced their visceral fat by over 13%. The heavy lifting group saw no statistically significant change in VAT.
How is that even possible? What is the mechanism linking a squeezed thigh muscle to fat loss around the liver?
The prevailing theory really comes back to the endocrine system. The intense hypoxia and acidity created by the cuff trigger a massive systemic release of catecholamines, things like adrenaline and noradrenaline, as well as growth hormone.
Yeah.
And visceral fat happens to be highly sensitive to those specific hormones, much more so than subcutaneous fat. So the localized stress of BFRT creates this systemic hormonal storm that acts like a heat-seeking missile for deep visceral fat.
It's like a surgical strike using your own hormones.
It beautifully illustrates that exercise isn't just one monolithic thing. The specific type of stress you apply dictates the bodily adaptation. Mechanical load yields one result. Metabolic stress yields a completely different one.
That's fascinating. I want to jump down to the genetic level really briefly because they did RNA sequencing too, right? What did the transcriptomics tell us?
The RNA sequencing just confirmed everything we've been talking about, but turned up to 11. The conventional heavy lifting group only had about 18 differentially expressed genes. The BFRT group, 110.
Wow, so the cuff creates a much louder signal at the genetic level.
Much louder. And when they looked at what those specific genes were doing, they were predominantly related to angiogenesis.
Which is the creation of new blood vessels, right?
Exactly. Genes like VEGF, vascular endothelial growth factor, were highly upregulated, which makes perfect intuitive sense. You are repeatedly starving this tissue of oxygen. The tissue panics and says, we need to build more highways to get oxygen-rich blood in here.
So it forces the body to build a better vascular network.
Yes, which leads to improved capillary density. For a diabetic patient who likely suffers from impaired peripheral circulation, forcing the body to grow new microvessels is a massive therapeutic win.
Okay, we definitely need to address the elephant in the room here. Safety.
Of course.
You are taking patients with type 2 diabetes, a population that often has fragile blood vessels, arterial plaque, or high blood pressure, and you are literally strapping a tourniquet to their limb and cutting off their circulation. Isn't that fundamentally dangerous?
It is always the very first question clinicians ask. But both in this specific study and broadly across the literature over the last decade, BFRT demonstrates a remarkable safety profile. In this trial, there were 0 adverse events.
What about their blood pressure, though? Doesn't inflating a cuff make your blood pressure spike dangerously?
During the actual exercise bout, yes, blood pressure increases, but importantly, it also spikes significantly during conventional heavy lifting.
Right, holding your breath while squatting will do that.
Exactly. But the critical metrics are the resting outcomes. After the 12 weeks, both groups saw a significant reduction in resting diastolic blood pressure and resting heart rate.
So long-term, their cardiovascular systems actually became less stressed and more efficient.
Correct. Now, there was one major metabolic metric that did not show a huge shift, and I think it's important we mention it to stay objective.
What was that?
Whole body insulin sensitivity. Despite the increased muscle mass, the new mitochondria, and the visceral fat loss, neither group saw a massive, statistically significant improvement in overall insulin sensitivity during the trial.
That feels completely counterintuitive. If you have more muscle to absorb glucose and less of the inflammatory visceral fat blocking the signal, shouldn't insulin function improve?
It absolutely should, and eventually it likely will. The consensus among the researchers is that 12 weeks is just a very short snapshot for that specific systemic change.
Oh, okay.
They've essentially poured the concrete and built a bigger, better factory.
Yeah.
The bad fat is being cleared out. But it might take another few months of training for that new machinery to fully shift the whole body metabolic baseline. It's a very promising watch, this space finding.
Makes sense. So zooming out and bringing this all back together, we kicked off this deep dive with a specific mission to understand this novel exercise intervention and to highlight the precise tools that validated it. For the clinician or the patient listening right now, what is the core takeaway?
The takeaway is that blood flow restriction training is a highly legitimate, potent therapeutic tool. It is not a fitness fad. It directly targets the specific physiological deficits of type 2 diabetes, mitochondrial dysfunction, and visceral fat accumulation in a way that traditional heavyweight lifting simply misses.
And for the scientists and lab researchers tuning in,
For them, the takeaway is a reminder that precision is everything. We would have absolutely no idea about the mitochondrial density changes in the muscle or, incredibly, in the adipose tissue without rigorous, absolute quantification.
right?
Utilizing verified, flawless standards like the OriGene RC23766 LPL plasmid and the SC11172 ND1 plasmid is literally what separates an interesting guess from a published scientific finding.
It's a fantastic reminder that behind every single groundbreaking paper, there is a foundation of incredibly reliable reagents. You simply can't build the house without the right bricks.
Well said. OriGene Technologies genuinely empowers that critical level of discovery.
Before we officially wrap up, I want to leave you, the listener, with something to chew on, something looking to the future. If we can maintain muscle mass and actually improve mitochondrial health without relying on heavy external weights, where does this go next? I mean, I'm thinking way beyond diabetes.
The potential applications are honestly staggering. Think about aerospace. An astronaut on a long-duration mission to Mars. In zero gravity, you can't lift heavy weights because heavy doesn't exist.
Right, their muscles just waste away.
Exactly. BFRT could be the key to maintaining their muscle mass and metabolic health in space because it relies entirely on internal chemical stress, not external gravity.
That is wild to think about. Or bringing it back to Earth, what about a grandmother recovering from a hip replacement? She obviously can't do heavy squats, but she could easily use a cuff and some light resistance bands while lying in bed to keep her metabolism firing.
Exactly. Post-operative rehab, geriatric care, bed rest studies, anywhere that mechanical loading is compromised or dangerous, this physiology can step in.
Yeah.
We are really just scratching the surface of how we can use localized metabolic stress as a systemic medicine.
It really is a brave new world of exercise science. Well, this has been an incredibly fascinating look into both the adaptive physiology of the human body and the advanced molecular technology that allows us to actually understand it.
It certainly has been. I really enjoyed this one.
I want to extend a huge thank you to our partners at OriGene Technologies for helping us bring this special deep dive to you. If you are a researcher looking for the specific plasmids we discussed today, the LPL or ND1 standards, please check the show notes. We've linked the original Trinks paper and the exact OriGene product details right there for you.
And remember, whether you are lifting heavy iron in the gym or lifting light weights with a cuff, the most important thing for your metabolic health is that you keep moving.
Absolutely. Thank you so much for listening to the OriGene Technologies podcast. Deep dive. We will see you all next time.
Goodbye, everyone.